All right, this is our last lesson in this unit, and it's not really any new concepts this time. It's more like we're just going to see how we can use amplitude and period and midline and all that stuff to help us fit a sine curve into some given situations. So we're going to be modeling some different things with sine cosine functions. So this first one says, in the classic novel Don Quixote, the title character famously battles a windmill. Suppose that the center of the windmill was 20 feet off the ground and the sails are 15 feet long. Don Quixote is caught on the tip of one of the sails, so as the sails are turning, and the sails are turning at a rate of one rotation every 60 seconds. So it spins around. And he's stuck on there, so he's just spinning around and around and around and around and around. Well, we can model his height above the ground as a function of time. So what we're going to do is we're going to sort of think about how high he will be at different times, and then from there we'll be able to make our graph of the function, and then we'll write the equation of the function. So, well, he gets stuck on the sail of the windmill down here near the bottom. So he's standing here, and then, as it goes by, he gets caught. So at time 0, at the beginning, at the very beginning, his height as he gets stuck on that sail is going to be 5 feet. So he starts down here at the very bottom. Now, as it spins around, you might maybe start thinking about, when will he be back down at the bottom? Well, it tells us that it rotates makes one full rotation every 60 seconds. So when he gets back down at the bottom, it's going to be here at 60 seconds, times 60 seconds. Okay, well, let's think about it then a little bit more. What else could we figure out? Well, if you think about it, if he starts here, when is he going to get to his highest point? Well, I think if the whole rotation takes 60 seconds, it should be pretty clear that he's going to reach his highest point after 30 seconds. Well, what is that highest point? How high is he going to be? Well, this height here, this little bit at the bottom is 5, and then we have a 15-foot sail. They're calling them sails. So that's how we know, and it also said that the center is at 20, and you can see that that 5 at the bottom and the 15 gives you the 20. And then he also is this high above, that's another 15. So I think his highest point, if you're just thinking through it logically, would be 35. So at 30 seconds, he's going to be 35 feet above the ground. And then you can see after 15 seconds, he would be halfway in between there because he's going at a constant rate, and then halfway in between the 30 seconds and the 60 seconds, he will be at the height of 20, the halfway height. That would be here, which is 20. Okay, so this would show you one cycle of the function, which represents one rotation of the windmill. But he keeps going around and around and around. So we can extend that pattern to fill in the rest of our coordinate plane here. So he's up high, down low, up high, down low. Okay, so here is our graph. So now let's answer some questions about this graph. Our first question is just, what's the midline of this thing, what's the amplitude, and what's the period? Well, we can see that the midline, which also corresponds to the center of the windmill, is 20 feet above the ground. The amplitude of the function tells us how high up it goes above the midline and how far down it dips below the midline, and it just repeats that over and over again. And here you can see that the amplitude is 15, which in our problem corresponds to the length of those sails that are spinning around. And the period of the function, well, the period would be the length of one cycle, And so this would be one cycle. So you can see that the period is 60 seconds. Well, somehow we need to convert that information into uh, an equation for this height above the ground. Well, looking at this one cycle that I have highlighted here, I'm hoping from prior work that you've done that you recognize that as a reflected cosine. And you could write it as a sine function. Definitely, you'd have to use a phase shift, but you definitely could write it as other types of function. Because I can see that minimum right on the y-axis, I'm going to write it as a reflected cosine. So it's going to be a negative something times the cosine. Up here, I'm going to write our equation so that we can sort of refer to it. Now, we don't have to use a phase shift here because that minimum is right on the y-axis. So I'm going to leave the phase shift out of the equation up that I just wrote there. So we need to translate our numbers into this function. So the negative something cosine, well, that something right there is the amplitude. So that's going to be a negative 15 cosine. And then we also have this midline of 20 feet. So this number at the end is going to be that 20 feet. Now we just need to figure out what b is. Something x, or something, I guess we should use t here since it's according to time. So remember that the period does not go directly into the equation. We have to always calculate what our b value is. Essentially, it's telling you how many cycles happen between 0 and 360 or between 0 and 2 pi. So we can calculate the b value, we talked about it last time, as either 2 pi divided by the period or 360 divided by the period. And I'm going to use 360. I'm going to go ahead and do this in degree mode, mostly because I noticed that that 60 will divide really nicely into the 360. So the b is going to be 360 divided by 60, and that means in my equation the b value is going to be 6. And if we evaluate this function, we're going to have to make sure we're in degree mode. So here is our equation. H of t is equal to negative 15 times the cosine of 6t plus 20. And remember, the 20 represents the midline. The negative 15, the 15 is the amplitude, and the negative tells us that it was reflected, so it starts at a minimum value. And the 6 here is our b value that relates to the period, and it tells us that the period is going to be 60 because we calculate 360 divided by 6. So that is the equation for this. Now let's read this last part. It says, after a minute and 40 seconds, Don Quixote falls off the sail straight down to the ground. Using your equation, how far did he fall? Well, our equation is in terms of time, negative 15 times the cosine of 6 times the time plus 20. So if we want to calculate his height, we need to know what time we're calculating that height. Well, our time is a minute and 40 seconds. Well, 1 minute is 60 seconds, so our time is going to be 100 seconds. So h of 100 is, our equation was negative 15 times the cosine of 6 times t, our t value is 100, plus 20. And we can put that into our calculator to calculate the height. Now, because I used 360 divided by b to calculate the period, or yeah, the b value, we need to make sure your calculator is in degree mode. If it's in radian mode, it will not give you a correct answer. Negative 15 times the cosine of 6 times 100, and then plus 20 in your calculator should give you a height of 27.5 feet. Our last question here says, does your answer agree with the graph? Does the graph agree with the solution? So let's look at the graph and see. at a height, at a time of 100, that's about right here between that 90 and that 105, what's the height of our function? And I think that that 27.5 we calculated agrees really nicely with the graph that we drew. About 27. Yep. Okay, next one. We're going to look at 3 of these scenarios. The ocean tides rise and fall periodically each day, and the time between high tides is approximately 12 hours. So that 12 hours between high tides. So if we're thinking about the height of the water, it's up high, then it lowers, and then it rises again. It's saying that that time between high tides is 12 hours. So hopefully you recognize that that is telling you that the period is 12. Okay. Next part says, oh, I lost the one. Oops. The next part says, at Joggins Wharf in Nova Scotia, the tide was found to be at its average height of 7 meters at midnight. So let's call time 0 midnight on that day. And then after that, the numbers will just be like 1 a.m., 2 a.m., 3 a.m., 4 a.m., and so forth. So it says at midnight, the height of the water, or the depth of the water, is 7 meters. It says at that point, the tide was rising, so it's going up, and it reaches its high point of 11.5 at 3 a.m. So here's 11.5 at 3 a.m. So it goes up, and then at that point, that's the high point, so that means it's going to turn down around after that. Now, it said 7 was the average height. So what that is telling you, the average of a trig function of a sine or a cosine, the average is the midline. So we have a midline of 7. And so this function, it looks to me like if it went up over the course of 3 hours, it should be back at its midline after 3 hours. But then it's not done. It's not going to immediately turn around. It keeps going down. 7 is the average, so it also has to go below that. Now, I could use the period here as well. I know that the cycle begins at a height of 7. It means that also ends at a height of 7 over here at 12. Halfway in between is where it's at its midline again, which we have shown. And then halfway in between here at the value 9, it should dip down, or the height should go lower by the same amount that it had raised above before. And we're talking about here the amplitude. So the amplitude, the amount it went up above its midline, is 4.5. So it should also go 4.5, 1, 2, 3, 4 and a half below the midline. So here's one cycle. And 4.5 was the amplitude. Okay, and then of course we could extend that pattern because our tide doesn't just go up and down once. It actually repeats that, of course, over and over and over again. Okay, something like this. So it says sketch the graph and write the equation. I do want to write the equation in just a minute, but I actually want to skip to part B and part C first, and then we'll write the equation. Part B says, when will the low tide be? So if we're starting at midnight, when will the next low tide be? It would be right here, and this is 9 on our x-axis. So this would be approximating 9 a.m. So our low tide would be at 9 a.m. How high will the tide be at 4 p.m. that afternoon? Well, if this is 9 a.m., this is noon. And this would be 1 p.m. So 4 p.m. would be 16 So we're thinking about how high the tide will be at 4 p.m. I would say it would be between 10 and 11. So maybe 10 and a half. And we are measuring in meters, 10 and a half meters. And we'll check that on our with our equation in just a second. So let's write an equation to fit this scenario. So I think if you notice these 5 points that we used as we were deciding the shape based on the information given to us, that this is a nice sine pattern right here. So we're going to write this function as a sine equation. So we'll have maybe y equals a times the sine. And again, there's not a phase shift here, so we'll just do b times t plus k. I didn't worry about having a phase shift in this. All right, so y equals, this first part is the amplitude, which we decided was 4.5. And it does go up first and then down, so it doesn't have a negative, it's not reflected. 4.5 times the sine of, we're going to have to figure out what b is, plus the midline is k. So b is the one that is a little bit harder to find because you have to calculate it. Well, we know the period is 12, so we can calculate b. b is equal to, and I'm going to go ahead and do it in degrees again, 360 over 12, which is the same as 30. So this is 4.5 times the sine of 30t plus 7, and that is, because I used 360, that is in degree mode. So let's go ahead and calculate that, and we'll actually put that time of 16 into the calculator. So in the calculator, if we evaluate it, it's 4.5 times the sine of 30 times 16 plus 7. If you type that into your calculator, we should get a number between 10 and 11 for that height of the water. And I get 10.89. So our approximation from the graph was pretty close to what we got from the equation that we wrote. Okay, one more of these. The monthly revenue for Otake's mower repair can be modeled by the function r of x equals 7.5 times this quantity of 30 times the quantity x minus 1 plus 12.5, where r of x is the average revenue in thousands of dollars for month x. X equals 1 is going to correspond to January. So on our x-axis, and it says to sketch the graph, and we'll answer some questions about it, but we need to know how to number our axis. Well, it looks to me like our x-axis can just be numbered with whole numbers here, 1 through until we run out of space, and each of these represents the next month. And so 13, of course, since December would be 12, 13 would represent the next January, 14 would represent the next February, and so forth. Okay, well, if we're going to sketch this graph from the equation, we need to first recognize where our midline is, and our midline is at 12.5. But we need to decide what scale to use. Should I put the 12.5 here? Should I put it over here? What type of scale? What sort of numbers do we want to put over there? Well, if we think about how high and low it's going to go above and below that midline, that can help us determine what numbers will work well. If the midline is 12.5, the maximum is going to happen above the midline by the amount of the amplitude. So the maximum is going to be 12.5 plus that amplitude of 7.5. In other words, the maximum is going to be 20. The minimum is going to be below the midline by that amplitude amount of 7.5. So the minimum is going to be 5. So my graph has to fit very nicely numbers between 20 and 5. So I think a good idea over here would just be to count by 5s. 5, 10, 15, 20, and 25. So if we sketch in that midline, we said the midline was going to be at 12.5. That would just be right here, in between the 10 and the 15, exactly halfway. All right, well, this is a sine function, so the pattern that we're going to use is beginning and middle, up, down. We need to decide where our beginning is going to be. Where does this thing start? So we have to check and see if it has a phase shift. And it turns out this one does have a phase shift. It's shifting it in the positive direction by 1 unit. So instead of starting here on the x-axis, or sorry, on the y-axis on the midline, it's going to start here, shifted 1 to the right. Okay, so we've got this point in our pattern. We figured out where this one is. Now we need to figure out where this ending point will go. And so to figure out where that one goes, we've got to consider the period of the function. Well, remember that the period is equal to 360 over b. And our b value from our equation is 30. So our period is 360 divided by 30, which happens to be 12. So the length of the period is 12. Well, if the period starts at the value 1 and has a length of 12, that means the cycle is going to end at the number 13. So the cycle ends all the way over here. If we find our halfway point so that we can mark this middle point here, that's going to be happening at 7. And now finally we need to use our amplitude to figure out how far up and down above that midline our function is going to go. And in this case, the amplitude is 7.5, and we kind of already talked about that the maximum value was 20. So here it goes up. And then the minimum value was 7.5 below the midline, so at 5. So here's one cycle of our function. And we can just sort of extend that over to show the rest of the function. So let's answer a couple of questions from this graph. Let's see, why does the graph have this shape? Well, this graph is showing the revenue for a lawn care mower repair service. So that shape, that up and down, sometimes they're busy and sometimes they are slow. Their business is sometimes slow. And what they call that is that this is a very seasonal business. Whoa, sorry. So it says, during which month does the company have the highest revenue? Well, their maximum value is right here, and that corresponds to number 4. Well, if this is January, February, March, number 4 corresponds with April. And probably the reason that April is their highest revenue month is that April is the time, March in St. George probably, but April for a lot of the country is when people are starting to get their mowers out, starting to get ready to start taking care of their yards for the summer, and they realize that, you know, as they try to use their mower, that it needs a repair. What is the average revenue per month overall? Well, the average of a sine function is the midline. So, you know, sometimes they make more money, sometimes they make less money, but the average amount that they make per month would be that midline, which is the 12.5. In the context of this problem, that would be $12,500. Okay, so today we didn't really do any new concepts. We just were trying to learn how to connect these ideas of graphing trig functions to some context, some real situations. So the homework assignment associated with this lesson has 4 problems for you to try to think about in context. Next time we are actually taking the test for first half of the class period, we will review, and I have our review available now if you want to start working on it early. So for the first half of class, we'll review and try to really solidify some of these ideas, and then we will have the test during the second half of the class period. And the test itself has only 10 questions, so it's not a long test at all. You should have plenty of time to do it. If you have questions before the test and you want to come in and talk to me about them, please do. I'm around almost all the time, except on Thursdays after school. So let me know if you need any extra help with this. Thank you.